underneath the desert moon. Silent night dust as a moon whispers in the cold tones, hidden secrets, ancient runes. Shadows dance upon the sand. Journey starts in unknown land. Footprints lost, no guiding hand. Dreams like tides, they shift and expand. Autumnal beer in the distance glows. Echoes of past where the wind blows. Autumnal beer through the night it flows. Spirit rides as the shadow grows.
In the world of physics land, sometimes walking isn't enough. Since the late 1800s, humans have traversed the expansive landscapes of the globe with speed, utility, and comfort in what we like to call the automobile. Today, we will be focusing on gasoline-powered cars, ranging from the absolute lowest of the low to the pinnacle of human engineering. We'll be looking at the physics, forces, and innovations of the cars on the road today.
What is at the heart of every car? In a conventional gas-powered car, the engine is what provides power to propel the car forward. The engine works by converting chemical energy stored in the gasoline into mechanical energy. The energy is harnessed using a fixed cylinder with a moving piston connected to a crankshaft. Gasoline is allowed into the cylinder, and by using spark plugs, it is ignited to create small, controlled explosions. The high-pressure gases created from the explosions push the piston, rotating the crankshaft. The most common type of gasoline engine is the 4-stroke engine. This is because each explosive cycle consists of 4 types of passes as the piston travels within the cylinder. These distinct processes are the intake, compression, combustion, or power stroke, and exhaust.
Oh yeah!
Modern gasoline engines have a capability of converting a maximum of 50% of the stored energy from gasoline or chemical energy into usable mechanical energy. Most gasoline cars on the road have an efficiency between 20 to 40%. Many engines are capable of higher efficiency, yet this would result in increased wear of the engine over time or emissions. Diesel engines routinely can achieve efficiencies of about 45% because of the higher compression ratios required in diesel engines. This is the energy diagram of a gasoline vehicle. This diagram is accurate, assuming that the chemical energy harnessed from the gasoline is converted at a rate of 50% efficiency to kinetic energy, which makes your vehicle move. The rest of the energy is considered energy loss and is represented by the thermal energy value. This accounts for all the energy lost due to heat, vibrations, and sound in the system. After the energy is producing rotational energy, it needs to be manipulated to the ideal speed. This is the job of the transmission. By using several different sized gears, a transmission can select the ideal ratio of torque multiplication for any situation.
Our first test will demonstrate how the horsepower from the engine and the mass of the vehicle affects the acceleration. We will be comparing a 1999 Pontiac Sunfire to a 2006 Suzuki GSX-R 1000.
Car crash, killing my entire family. Kids gone in flames, their bodies unrecognizable. Car crash, killing my entire family. Kids gone in flames, their bodies unrecognizable.
Looking at the results after the race, the bike accelerated much faster than the car. Does this mean that the bike has more horsepower? In actuality, the bike and the car have almost the same amount of horsepower, so how did the bike accelerate faster? If If we look at this equation for force, force equals mass times acceleration. If we rearrange the formula for acceleration, and we have the same amount of force being the horsepower, the bike's lighter mass contributes to the greater acceleration, as the force is being divided by a smaller amount of mass.
Wheels could be considered the most important part of the car. They could be thought as the shoe of the car, allowing the vehicle to change speed or direction at will or with velocity. They are responsible for transmitting the torque from the engine into the ground. This is all done using friction. Rubber and concrete has one of the highest mu values of 1.0. This means the friction force applied to each tire on your vehicle is proportional to 1.0 of the normal force experienced by each wheel. The specific coefficient of friction for everyone's vehicle is slightly different because of the weight distribution of the car, the manufacturers and design of the wheels, and the quality of the wheels.
To demonstrate the importance of the wheels and tires of a car, we will be performing a test between two of the exact same cars, only differing in their wheels and tires. We will be looking at the lap times and G-force meters to see any differences in their handling and characteristics. Looking at the first corner, we can see that the high grip tires put out a max of 1.3 Gs laterally. Meanwhile, the left side put out 0.93 Gs laterally. Very poor performance.
I passed it.
As you can see, even with the exact same cars, a difference in tires has made a 20% difference in lap times.
Okay, neutral. But what happens when things don't go to plan? Approximately 1.19 million people die each year as a result of road traffic crashes, and over 50 million are injured. But what is the deadly physics in a car accident? When they say speed kills, they are totally wrong. There are multiple factors or variables that are involved. If we go back to our original equation, F equals ma, we can see clearly the relationship between force, mass, and acceleration. So what is the safest vehicle to be in a car crash? We will now demonstrate how changing these variables affects a car accident.
Okay, neutral. 3.31.
9.8.
Here's a spreadsheet of the car crash testing. As we can see, the average force experienced by both vehicles is around the same. However, the G-force, or acceleration, is way higher on the lighter car than the heavier car. The lighter car had an average acceleration of 90.76 meters per second squared, while the heavier vehicle had an average acceleration of 33.31 meters per second squared. In conclusion, the heavier vehicle is a much safer option when in collision with a lighter vehicle. Acceleration is what kills, not the force.